So the past week or so, we were talking about what is pressure, what is temperature, and yesterday in the lab, you kind of got introduced. Okay, what is volume? The amount of space of something, and we were kind of talking about okay, well, what's the relationship between them? Does pressure goes up as volume goes up, or vice versa, and all that good stuff? Well, those ideas are demonstrated through gas laws, and that's what we're going to be talking about today. Now, there are four different types of gas laws that show the relationship between pressure, volume, temperature, and the amount of gas. Specifically, this idea helped produce four gas laws.
Our first gas law is Boyle's law, and Boyle's law is P1 times V1 equals P2 times V2. Now, 1 and 2, think of it before and then after. Before a reaction, something happened, then 2 is after the resulting. So you're going to have two pressures and two volumes. Now, this type of equation represents an inverse proportion. And what I mean by inverse proportion is if the pressure goes up, the volume goes down, or if the pressure goes down, the volume goes up. So think about oppositely. So with that idea, this Boyle's law graph kind of looks like a upside down exponential function, just like in a curve going down. So make sure you know the equation, inverse proportion, all of that. Okay. Gas law number 2 is Charles' law. Charles' law equation is V1 divided by T1 equals V2 divided by T2. Again, 1 is before, 2 is after. Now, this law represents a direct proportion. And what I mean by direct proportion is if volume goes up, temperature goes up, or volume goes down, temperature goes down. And Charles' law equation looks like this. It's just a straight positive linear line. Gas law number 3 is Gay-Lussac's law. And Gay-Lussac's law equation is P1 divided by T1 equals P2 divided by T2. Again, 1 is before, 2 is after. And this also has a direct proportion. So if pressure goes up, temperature goes up, or if pressure goes down, temperature goes down. And this graph probably looks very similar to Charles' law because it is, again, a positive linear slope graph. Our last gas law is going to be Avogadro's law. Now, we've heard about Avogadro before, avocado, the 6.022 times 10 to the 23rd number. Now, he also has his own gas law as well, and that says that volume 1 divided by moles 1 equals volume 2 divided by moles 2. Again, 1 is before, 2 is after. And this again also represents a direct proportion. So as volume goes up, moles goes up, and as volume goes down, moles goes down. And again, the graph's going to look very similar to Charles and Gay-Lussac's law because it's again a positive slope linear graph. All right, so make sure you know the different types of gas laws, the equation, direct or inverse, the graph, and all that good stuff.
Alrighty, so let's go ahead and do some practice problems of using the four different types of gas laws. So our first problem we're going to do, it says the pressure of oxygen gas rises from 886 mmHg to 241.4 kPa. If the initial temperature is 360 K, what is the final temperature? So, like any other problem, we're going to have to go ahead and circle what we are given and underline what are we trying to find. So, we are given three numbers with three units. We are given 786 mmHg, 241.4 kPa, and then the 360 Kelvin. And the problem is asking us to find the final temperature. So So the way we're going to always start off these problems is we're going to go ahead and make a box. The box is going to look like this. That's how the box is going to look like. So we have pressure, volume, N, which is our amount of gas, and then R, and then that R is supposed to be T. My apologies. And then we have T for temperature. And then we have 1 and 2. 1 represents initial, and then 2 represents our final. So now we're going to take the numbers that we are given and put them in our box. So we have the pressure rises from this to this. Since we know mmHg and kPi are units of pressure, we know these two are our pressures. If we're given two pressures, two volumes, two temperatures, or any of that stuff, we are always going to know that, okay, since we're given two, the first one is going to be our 1 and the second one is going to be our 2. Okay, so since this is going to be our first pressure, our first pressure given, this is going to be P1. And since this is our second pressure given, this is going to be our P2. So we're going to put this number in unit in our P1. And since this is our P2, we're going to put this in pressure 2. And then we have, if the initial temperature is 360 K, remember initial's 1, and this is our temperature, that means this is going to be our T1. So we're going to put that in our 1 T1. And then it says, what is the final temperature? Remember, final is 2. We need to find final temperature. So we need to find T2. Now, we are not given anything about volume or about moles, so we're going to cancel that out. So there is an equation which is combining all four of our gas laws, and it's called a combined gas law, which is that. Since we are not given anything in volume or moles, we can cancel out volume and our moles. So the equation we're going to use is our P1 over T1 equals our P2 over T2. So now we're going to plug in all the information. Well, first, before we do that, we got to make sure, are the new units the same? Well, we don't know the other numbers, so that's good. But our units is not the same here. We have mmHg and then we have kPa. We have to make these units the same before we plug this into the equation. So you can either convert mmHg to kPa, or you can convert kPa to mmHg. So let's just go ahead and convert kPa to mmHg. So we're going to convert this to mmHg. So we have we're starting with kPa, we're given kPa, but we want to find mmHg. Since we're given kPa, kPa is going to be on the bottom. And since we want mmHg, mmHg is going to be on the top. So now that we did that, we can figure out what numbers. So remember that 760 goes with MMHG, and that 101.3 goes with KPA. So now our KPAs cancel, so we can go ahead and do our calculation. So we're going to multiply the top, divide the bottom. So we're going to go ahead and do our 241.4 times our top, which is our 760, divided by our bottom, which is 101.3. So when you do that, you get MMHG, and that is our 241.4. So that's what we're going to plug into our problem. So now that we have MMHG, the same unit, we can go ahead and start plugging into the leftover problem. So our pressure 1 is our 786. Our temperature 1 is our 360. We got our equal sign. And our pressure 2 is what we just calculated, our 1812. And like we said, we don't know our temperature 2, so we're just going to rewrite that. That's what we need to solve for. So now this is proportions. So how you're going to deal with proportions is you're going to multiply the top, like crisscross it. So we're going to do 786 times T2. And since we know that we're just going to multiply these two, 360 times 18.2, so let's go ahead and do that. 360 times 1812, get 652,320. Very, very, very big number. Now we got to solve for T. We got to get T by itself. So we're just going to divide 860 to both sides. 786. Sorry, I'm saying all these numbers completely wrong. So when you do the 65230 divided by 786, you get your T2 to be 830. And we know our unit's Kelvin because our first temperature here, our T1, is in unit Kelvin. Now, you don't need to worry about rounding or significant figures, so just round whatever number you would like to round for these types of problems. So don't worry about that, but that is your final answer. Okay, so now we have the volume of chlorine gas drops from 1.45 liters of 3.8 to 3.8 liters. If the initial amount of gas is 1.70 moles, what is the final amount of gas? Again, always these problems, we're going to circle what we're given, and we're going to underline what the problem's asking us to find. So we're given our 1.45 liters, our 3.80 liters, our 1.70 moles, and the problem says, what is the final amount of gas? So it wants us to find the final amount of gas. Okay. So we got to figure out, is this going to be pressure 1, pressure 2, volume 1, value 2, mole 1, mole 2, all that good stuff? Well, we're given 2 liters. It says 1.45 to 3.80. That means this is going to be number 1, and this is going to be number 2. So this is going to be volume 1, and this is going to be volume 2. Right? Because it says this to this. So 1, 2, and then 2. And then it says the initial amount of gas is 1.70 moles. Remember, initials 1, this is going to be 1 mole, which mole is also represented as N. So this is going to be N1. And it says we have to find the final amount of gas. Remember, final is 2, and this is the amount of gas, which is N, the variable N, so it's going to be N2. So going back to our table again, so redoing our table. Let's go ahead and fill these into our respective tables. So we know this is going to be V1, so we're going to put that here. This is our V2. This is our N1. And we don't know our N2. So now we got to figure out, are the units the same in each row? Liters, liters, so that's good. Moles, we don't know, so that is good. So we're good with our units. So let's go ahead and look at that combined gas law equation. Now, we are not given anything for pressure or anything for temperature. Since we're not given anything for pressure and temperature, we just cross it out. So we have V1 over N1 equals V2 over N2 is the equation we're going to use with our variables. So let's go ahead and plug all those in. So our V1 is our 1.45. Our N1 is our 1.7. And our V2 is our 3.80. And again, we do not know our N2, so we're just going to rewrite N2. Again, this is proportion. We got a fraction equal fraction, so we're going to cross multiply. We're going to cross multiply. So we're going to do that 1.45 times our N2. Since we don't know what N2 is, we're just going to rewrite that, timesing our N2. And then we have our equal sign. And we're going to cross multiply these, 1.70 times 3.8. Since they're both numbers, we could just already go ahead and do that. And we get 6.46. So now we have to get N2 by itself. So we're going to go ahead and divide 1.45 to both sides. That cancels. So what we're left with for our final answer is when we do 6.46 divided by 1.45, we get 4.46. And since our initial unit was moles, our final will have to be moles as well. And that is your final answer. Again, you do not need to worry about rounding for these problems. Okay, so let's go ahead and do another one of these problems. Now, this time we have the temperature of hydrogen gas rises from 18 degrees Celsius to 45 degrees Celsius. If the initial volume of gas is 2.75 liters, what is the final volume? Again, first things first, we're going to do with these types of problems. Circle what we're given and underline what we are trying to find. So we have 18 degrees Celsius, 45 degrees Celsius, 2.75 liters. And it says, what is the final volume? Well, we got to find the final volume. Now we have two temperatures here. So it says it rises from 18 degrees Celsius to 45 degrees Celsius. So this is from and this is to, meaning this is going to be our initial and our final. So it's going to be 1 and 2. So it's going to be T1 and then we got T2. And then it says if the initial volume of gas is 2.75, since this is our initial, we know initial is 1, and we know this is volume, this is going to be our V1. And then the problem's asking us to find the final volume. We know final is number 2, so this is going to be our V2. So let's go ahead and make our chart again. Alrighty, and now let's go ahead and put all our numbers in here to the chart. So our T1 is 18 degrees Celsius. T2 is 45 degrees Celsius. Our V1 is 2.75 liters. But we don't know our V2, so it's going to be a question mark. So now we got to figure out, are we in the right units? Well, we don't know the other liters, so that should be fine. Now, these are both degrees Celsius, okay? Now, and they're the same units, so you're going to say, okay, we don't need to do any conversions. But we're going to need to do conversions for this one because temperature needs to be in Kelvin always. It needs to be in Kelvin always. And remember, that is just adding 2.75 to both of these numbers so we can get both of them as Kelvin. So let's go ahead and do that. So we're going to take 18 degrees Celsius. We're going to add 273 to it. So when you do that, we get 291 Kelvin. So let's go ahead and do that. And then now we have to do it again for our 45 degrees Celsius. And we get 318. So now that our temperatures are in Kelvin, which they always have to be, and then we're good here, we can go ahead and figure out of our combined gas laws what is going to be our equation we're going to need to use. So our combined gas law is P1 V1 over N1 T1 equals P2 V2 over N2 T2. So in our chart right now, we have nothing for pressure and we have nothing for N. So we just cross that out. No pressure, no N, no pressure, no N. So what we're left with is V1 over T1 equals V2 over T2. So we just go ahead and plug in what we know for those. So our V1 is our 2.75. Our T1 is our 291. Our V2, we do not know our V2, so it's going to be a question mark. Not a question mark, we're going to rewrite V2. And our T2 is our 318K. So now we can go ahead and do, since it's fraction equals fraction, we can go ahead and do our cross multiplications. So I always like to start with the cross multiplication with the variable, which what we don't know, so we just have to rewrite that. And then we have 2.75 times 318. So let's go ahead and do that. 2.75 times 318. And we get 874.5. So now we have to get V2 by itself. So we're just going to divide 291 to both sides. And when you do that, you get V2 will equal 3.01. Our initial unit was liters, so our final unit has to be liters as well. And that is your final answer for this problem. So let's go ahead and do one last problem of this before I have you guys do them on your own. So this time we have the pressure of nitrogen gas drops from 315 kPa to 311 atm. If the initial volume of the gas is 1.4 liters, what is the final volume? Again, for these problems, we got to figure out what are we given, circle what we are given, and underline what are we trying to find. Well, we're given 3.15 kPa, 3.11 atm, and 1.4 liters. And it says, what is the final volume? So we got to find our final volume. So now that we know what we're given and what we're trying to find, we can go ahead and look at those and figure out what variable they are. Well, we have two pressures, okay? It says drops from and then to. That means this is our first pressure and this is our second, so initial and final. That means this is going to be our P1 then, and then our P2. And then it says the initial volume of the gas is 1.4 liters. Initials, remember, is number 1, and this is volume, so we got V1. And the problem wants us to find the final volume. Remember, final is number 2, so we have to find V2. So now we know all that, we can go ahead and make our chart and fill that in. So we have our P1 is our 315 kPa. And our P2 is 3.11 ATM. Our V1 is 1.4 liters. And we don't know our final, so we're going to do a question mark for that one. So now we got to go ahead and figure out our units. Are they the same? Well, we don't have another volume, so we're good with that. But we have kPa and ATM. They're not the same units, so we're going to have to do some sort of conversions. We can convert kPa to ATM, or we can do ATM to kPa. Let's go ahead and do the 3.11 ATM and convert that to kPa. ATM, so we got to do our times in a line. Since we are given ATM, we need to find kPa. Since we're given ATM, that's going to be on the bottom. And we need to find kPa, so kPa is going to be on the top. The number for ATM is 1, and the number for kPa is 101.3. And our ATMs cancel. So you're going to multiply the top, divide the bottom. So you're going to go ahead and do 3.11 times 101.3 divided by 1. And you are going to get 315 kPa. So that is what's going to be representing here. So let's go ahead and plug into to figure out, using our combined gas law to figure out what our equation is. So our combined gas law is that. So we are not given anything for N or anything for temperature, so we can just go ahead and cross those out. So what we're left with is P1 times V1 equals P2 times V2. So let's go ahead and plug it in. So our P1 is 315. Our V1 is our 114, our 1.4 equals our P2 is our 315. And our V2, we don't know, so we got to rewrite it. So now we have to get V2 by itself, so we just have to divide 315 to both sides. Sorry, this is 315. So when you go ahead and solve that, you take the 315 times our 1.4 divided by our 315. I'm sorry if I'm writing 4s. It's 315. You get 1.4. Our initial volume unit was liters, so our final will have to be liters as well. And that is your final answer. Okay, so why don't you go ahead and do these problems on your own. So the first one says the volume of fluorine gas drops from 12 liters to 7 liters. If the initial temperature is 226 degrees Celsius, what is the final temperature? Alrighty, and here's your answer. Alright, go ahead and do this problem on your own. The pressure of a methane gas rises from 0.789 atm to 783 mmHg. If the initial temperature is 320 Kelvin, what is the final temperature? Alrighty, and here's your answer. Alright, that's it guys. Thanks.